Homework solution 4.4. A 50 MVA, 30 kV, 60 Hz synchronous generator has a synchronous reactance of 9 ohms per phase and negligible resistance. The generator is delivering rated power at 0.8 power factor lagging at the rated terminal voltage. Determine the excitation voltage per phase and the power angle. And if the generator is operating at the excitation voltage of A, what is the steady state maximum power the machine can deliver before losing synchronism? Find the armature current and power factor corresponding to this maximum power. The givens in this problem statement are the three-phase power magnitude. S3 phase is equal to 50 MVA. The terminal voltage magnitude is equal to 30 kV over root 3. The electrical frequency is 60 Hertz. The synchronous reactance is 9 ohms. The armature resistance is 0 ohms. And the power factor equals 0.8. We are asked to find excitation voltage, which is EF, and the power angle, which is delta. And then we're asked to determine the maximum power the machine can provide before losing synchronism, the armature current, and the power factor at Pmax right there. So the solution to this, again, just goes back to the circuit model. We've got the generator circuit model here, excitation voltage, and I guess maybe we'll write it in its complete form. Excitation voltage at angle delta. We've got XS, we've got RA, we've got magnitude of IA at angle minus whatever the power factor angle is. We've got a load, which determines this power factor angle and the amount of current that's being drawn. And we've got the terminal voltage, which is typically taken as the reference voltage. So that's the circuit model. And so the first thing is determine the excitation voltage per phase and the power angle. So we just extract that from the power information. We use power information and terminal voltage to get current, and we can use that to then solve for EF. We've done that before. The next part is if the generator is operating in the excitation voltage of A, what's the steady state maximum power the machine can deliver before losing synchronism? So what happens is as the amount of power drawn from this generator increases, the power angle is going to get closer and closer to 90 degrees. Once that thing reaches 90 degrees, the generator can no longer maintain synchronism between the rotor field and the armature field, and so that's what we call the maximum steady state stability limit is when that delta gets greater than 90. So we got to figure out when that happens. So once we figure that out, we want to know, well, what's the armature current and power factor that caused that to happen. So that's the solution method, is figuring that all out. In the first part, we were asked to determine EF, so we would just want to draw the equation for this, and that's going to be EF is equal to the terminal voltage here plus the voltage drop across those elements, IA times J XS in this case, since RA is 0. I guess we could make that look like a phasor diagram if we wanted to. That's VT. This was a lagging system, so that's IA, that's phi, and then we've just got VXS because there is no voltage drop across the resistance since it's 0, and that is EF, and that's delta. So phasor diagram, circuit model, Kirchhoff's voltage law. To solve this, we need to know what IA is. So we've got phase power divided by VT, complex conjugate, and I know that S phase is equal to 50 MVA over 3. I got to determine what its angle was. That's the inverse, so at angle phi, and phi is equal to the inverse cosine of the power factor, which was 0.8, so it's 36.87 degrees. And then the terminal voltage was given as 30 kVA over root 3. So the armature current is going to be 50 e to the 6 over 3 at an angle of 36.87 degrees. Divide that by the terminal voltage, which was 30 e to the third over root 3. And then I need to take the complex conjugate of that. And I get 962.25 at an angle of negative 36.87 degrees amps as my armature current. So now I can just plug this into this equation right here to determine what my excitation voltage and power angle are. That's going to be 30 e to the 3 over root 3, angle 0 degrees, plus 962.25, angle negative 36.87, times the J9 here, and that gives me 23,558.4 at an angle of 17.1 degrees volts. So I can extract the magnitude of the excitation voltage, EF, is 23,558.4, and the power angle delta is 17.1 degrees. So that answers part A here. So moving on to B, what we were asked to determine was, well, what is the maximum output power? And the formula for that, you can just remember that the output power formula is the magnitude of Vt times the magnitude of the excitation voltage, so the magnitude of terminal voltage times the magnitude of the excitation voltage, divided by the synchronous reactance. Now this formula is an approximation for when XS is much larger than RA, which in this case it is because RA is 0. So we get Vt, which we just calculated, or was given to us as 30 e to the third over root 3. We just calculated the magnitude of EF, 23,558.4, and then XS was 9 ohms. Notice that's not JXS, it's just XS. And that gives us 45.34 megawatts. Notice these are per phase units, so that's per phase, and so Pmax 3-phase is equal to 3 Pmax. I guess we could call that phase if we wanted to be clear. And so that gives me the maximum output power is 136.014 megawatts. And I guess where this came from was that P out per phase is equal to magnitude of Vt, magnitude of EF, XS times the sine of delta. So we had that formula. This is, refer to your notes for where this formula comes from. But this tells you the output power if you know the excitation voltage and the terminal voltage and the synchronous reactance of the device. So how much power is directly proportional to the sine of the power angle, and we know that you'll get maximum power when delta equals 90 degrees right there. So that's when the maximum power occurs. So synchronism is lost when above that angle. So that's the maximum power that will occur before synchronism is lost, and we know that the angle between the rotor field and the stator field can't be larger than 90, or else synchronism will be lost in a synchronous generator. And so the last part of the problem asks us to determine the current and power factor when that occurs. And so what we've got is this situation. Sorry, that's not V, that should be a Z load. This guy's going to be 23,558.4 at an angle of 90 degrees. That is IA. And this is VT, and this is XS. So we can say that the IA is going to be EF minus VT divided by XS. So it's just current through this inductor has to be equal to the voltage across the inductor divided by its impedance. So it's IA is equal to EF minus VT over its impedance JXS. So that's 23,558.4 at an angle of 90 degrees minus 30 e to the third over root 3 at an angle of 0 degrees for VT. Divide that by J9. So we get IA is equal to 3,248.93 at an angle of 36.32 degrees amps. And that means the power factor is equal to the cosine of 36.32 degrees is 0.806. And the magnitude of the current is 3248.93 amps. So that is the current magnitude and power factor at which synchronism is lost in this synchronous generator.